All right, so I am going to start where we hopefully left off on section 3.4 or page 26 of the handouts. So this is measures of position and outliers. So in this section we're going to talk about measures of position. And the whole point here is they describe the relative position of a certain data value within the entire set of data. Okay, and this is just useful if you want to know where is a particular data set relative to the rest of the data set. Is it right in the middle with the rest of the herd? Is it a fairly typical data value? Or is it out on the edges, very low or very high, one of the potentially extreme values? So one thing that we use to evaluate this is called z-scores. So z-scores are just standardized values. It equals the number of standard deviations that a given data value is above or below the mean of the data set. So you're basically just comparing one particular data value to the mean of the entire data set. If your z-score is greater than the mean, then it will be positive. If it is less than the mean, then it will be negative. And the thing that we use z-scores for is to identify unusual data values. Okay, unusual. Either unusually small or unusually large. All right, so to calculate the z-score for a particular data value, assuming you just have sample data, then z is equal to x minus x bar divided by s. Okay, so where x is the particular data value, and then you're subtracting the sample mean and you're dividing by the sample standard deviation. All right, now if you're talking about a whole population, then the z-score is equal to x, again, just the particular data value, minus mu, which is the mean of the population data, divided by sigma, which is the standard deviation of the population. Now, for reasons that will become obvious another chapter or two on, we will always round our z-scores off to 2 decimal places. Okay, so we are essentially creating a new standardized distribution, and by doing this, z-scores allow us to compare values from different data sets by providing a standard basis of comparison. All right, I'm going to erase this and go on to the next page. So for example, comparing standardized test scores. All right, so let's say there's a college admissions office and need to compare students who took either the SAT or the ACT. All right, so among the applicants who took the SAT, the mean is 1,500, the standard deviation is 240. For those who took the ACT, the scores have a mean of 21 and a standard deviation of 6. Okay. So some guy Mike applies, he got a 1740 on the SAT. Another guy Packard applies, he got a 30 on the ACT. So 2 totally different distributions. So how do we evaluate who did better on their test? So the only way to evaluate is to standardize the comparison by calculating the z-scores. All right, so for Mike, the z-score is going to be his data value, and his data value was 1740. Oh, crap. Sorry, I don't know how to make that stop. Is there a way? Okay, don't show this message again. Got it. Sorry about that. His data value was 1740, and then minus the mean for the SAT, which was 1500, and then divided by the standard deviation for the SAT, which was 240. Okay. And if you do that calculation, and do go ahead and do that calculation on your calculator, make sure you're doing it correctly, because when you do this, probably what you need to do is put parens around the numerator and then do the division, divide by 240. So you should get exactly 1.0. So that means that Mike scored exactly 1 standard deviation above the mean. All right, so for Packard, his data value was 30. All right, so his z-score is going to be 30 minus the mean, which was 21, and then divided by the standard deviation, which was 6. And again, go ahead and calculate this, and you should see that it is exactly 1.5. Okay. So the point is, Packard's z-score is higher. Okay. He did better relative to the population of the ACT test takers than Mike did relative to his population of SAT takers. All right. All right, I'm going to erase this and scooch down so we can look at the graph. So what we've got here then basically is, say for the SAT, the mean right here in the middle was 1500. For the ACT, the mean, again, right in the middle of the normal distribution was 21. Okay. And then what we are doing is we are normalizing by calculating z-scores. And if you are exactly 1 standard deviation above the mean, your z-score is 1. If you're exactly 2 standard deviations above the mean, your z-score is 2. If you're right in the middle on the mean, your z-score is 0, and so on. -1 and -2. Okay. And then what we just saw was that Mike's z-score was 1, right here, and Packard's z-score was right here, 1.5. Okay, so relatively, he did better. All right, I'm going to erase, go on to the next page. So how can we use these z-scores to identify outliers, data values that are far away from the rest of the data? Okay. So this method only applies to distributions that are fairly bell-shaped. Okay, bell-shaped. Because this whole method is based on the empirical rule, which assumes that the data distribution is bell-shaped. Okay. So within a particular data set, the z-score gives us a good idea of the relative standing of a particular data value. You know, if your z-score is fairly close to 0, that means that it is close to the mean. Okay, it's right there in the middle. Okay, it's close to the mean, which means that it is a very typical data value, a very usual data value. It's right there in the middle with the rest of the data. Okay. However, if a data value has a z-score of less than -2 or greater than positive 2, that means it is very far away from the mean. It's far away, it's out on the edges. It's far away from most of the data values. So that would mean that it is, less typical of a data value. Just scooch down a little. So here's kind of just a scale of z-scores. So 0, again, is just right in the middle. That's where the mean is, right in the middle of the bell-shaped curve. That is very ordinary. That's where we expect the data to be. However, if you're out here, if you're greater than a z-score of 2, or if you're less than a z-score of -2, then you're very far away. Look, I mean, there's just a little data down here. There's just a little data up here. Most of the data is here. Okay, that's the ordinary or the usual data. So specifically, ordinary or usual data values are defined to have a z-score between -2 and +2. Okay, so in other words, anything in this range between -2 and +2, that's an ordinary data value. It's in there in the middle with the rest of the data. However, if the z-score for your data value is less than -2, or if it is greater than +2, in other words, if you're down here or if you're up here, that's very far away. So that is considered to be unusual. Right, I'm going to pause for just a sec. All right, so let's resume, and now we are talking about percentiles and quartiles. Okay, these are just more descriptive statistics, and let's start by talking about percentiles. And I'm sure that everyone at some point in their life has heard of percentiles, probably in school when you took standardized testing. They always report back what percentile you were in. And just a note right off the bat is that percentiles are a resistant data measure. Okay, resistant. They are not affected by extreme values. So, what are they? They're numbers that divide a data set into approximately 100 equal parts, okay, with about 1% of the data in each part. So you have a whole data set, however many data values, and you're going to split it up into about 100 parts. Okay, so a data set has a total of 99 percentiles. So starting with the first percentile, which we would write as P sub 1, and then P sub 2, and so on, all the way up to P sub 99. Okay, because you only need 99 percentiles to split it into 100 parts. So we would call it the kth percentile. The interpretation of that, the kth percentile, means that k percent of the data values, the observations, are less than or equal to the observation. So for example, if you're talking about the 20th percentile, we would write it like this, P sub 20. So that means the 20th percentile. Okay. So in other words, about 20% of the data values would be less than that one, and about 80% of the data values would be greater than that. Okay? So if you're in the 20th percentile, then you're closer to the bottom than you are to the top. Okay? So just for example, here, assume that you had a data set that had exactly 500 data values in it, and you've got them sorted in ascending order, so from smallest to biggest. And in this case, you would have exactly 5 data values in each part. The percentiles would divide it into 100 groups, 5 data values in each group. So say you would have the smallest data value, the first, second, third, fourth, and fifth. And then right here would be the value of your first percentile, P1. 6, 7, 8, 9, 10, the next 5. And then right here would be the value of the second percentile. And so on until you get all the way up here where you would have your 99th percentile. And then just above that you would have the top 5 data values. Okay? So in other words, down here you have the bottom 1% of the data, and above it you have the top 99% of the data. Or you could think of it like this: the values on the top here are the top 1% of the data, and below it you have the bottom 99% of the data. Okay. So based on this definition of percentiles, then we are going to come and define our quartiles. Okay, I'm going to erase and scooch down. All right, so the quartiles are essentially percentiles, but they are particular percentiles, values that divide the data into 4 groups. All right, so there are 3 quartiles, Q1, Q2, and Q3, because we only need 3 quartiles to divide the data into 4 parts. So it basically looks like this down here. We've got the bottom 25% of the observations, and then we have Q1, the first quartile. Here we have the bottom 50% of the observations. And then right in the middle, we have the second quartile, Q2, which is actually exactly the same as the median, which we already know how to find. It's the data value right in the middle of the data set. All right? And then you have another 25%, and then you have the third quartile, and then you have the top 25% of the data values. So again, these are sorted in order. You've got the smallest value down here. Everything is arranged in increasing order. You've got the biggest value here. Okay? So the data has to be sorted in ascending order. Q1, the first quartile, separates the bottom 25% of the data values. Okay? Q2, like I just said, is the median, which we already know about, the median. It's physically the middle value. It separates the bottom 50% of the data from the top 50%. And Q3 separates the top 25%. All right, going to erase and go on. Okay, so this is just a nice figure, I think. I'm not sure if it's from our book or a previous book. Basically showing the quartiles for the 4 common distribution types. Uniform, where all the data is equally distributed. So basically, you've just got a rectangle divided into 4 equal areas. Bell-shaped, you can see, here's the middle, here's 25%, here's 25%. Then you've got a long tail, each with 25%. Right skewed, again, you can just kind of see how it's distributed. Same with the left skewed. Okay. And just a note that the 25% in each case refers not only to the number of data values, but it's also equivalent to the area under the curve, because we will, start talking about that in another couple of chapters. So, for example, this 25% represents 25% of the area under the curve. All right, and then just for information on how do you actually find the quartiles, here's the definition straight out of the book. Start by arranging your data in ascending order, smallest to largest. The easiest is first find the median, which is the same as the second quartile, and we already know how to do that, depending on whether there's an odd or even number of data values. And then third, basically divide the data set into halves. The data values below the median and the data values above the median. The first quartile, Q1, is the median of the bottom half. The third quartile is the median of the top half. Okay, now, just a note, if you have an odd number of data values in your data set, then you do not include the median, which would be the exact middle value in the data set when you're determining Q1 and Q3. Okay, so in this case, there is one middle value and you do not include it in the bottom half or the top half. Okay, I will show you an example of both ways. And also, just a note, like the percentiles, the quartiles are a resistant measure. Okay, they are resistant to extreme values, which is why we like to use them, particularly if there are extreme values, if the data set is very skewed. All right, let's go on and look at some examples. All right, so assuming that we have an even number of data values, they've already been sorted smallest to largest. Okay, so we know in this case, so there's 12 data values, 1, 2, 3, 4, 5, 6, exactly halfway. 1, 2, 3, 4, 5, 6. All right. So Q2 is always easy to find because it's the median, which in this case we know is going to be the mean of these two numbers. In other words, I need to take the mean, so I need to do 17 plus 24 divided by 2, which is equal to 20.5. So the second quartile equals 20.5. All right. And then if you go back and read again the definition on how to find, say, Q1, the median of the bottom half of the data. So in this case, Q2 is not even involved. We just want to find the median of the bottom half, which is this. 1, 2, 3, 4, 5, 6. Again, it's an even number. So the median of those 6 numbers is going to be right in the middle here. Okay. So it's going to be the mean of these two numbers. In other words, 6 plus 10 divided by 2, or 8. Same for finding Q3, the median of the top half. So now I'm just going to consider this part of the data set, which again is even 1, 2, 3, 4, 5, 6. So the median of that is going to be right in the middle of those two. And the mean of these two values, 27 plus 28 divided by 2, will be 27.5. Okay. All right, so just to make sure we're clear, let's go through another example where we have an odd number of data values. So now we only have 11, so that's like having 5 on the bottom, 1, 2, 3, 4, 5. This is exactly in the middle, 1, 2, 3, 4, 5 on the top. All right, so Q2 is that number that is exactly in the middle, which is 24. Okay. And again, if you look back at the definition for Q1, the median of the bottom half, not including the median. So not including this value. So in other words, just looking at these 5. What is the median of those 5 data values? Well, it's odd. So again, we have a data value exactly in the middle, which is 10. So Q1 is 10. And then same on the top half, we just look at these 5 data values. And Q3 is going to be the median of those, which would be the data value right in the middle, which would be 28. Okay. All right, I'm going to erase. And just a couple comments down here that there is not just one way to find the quartiles, which is a little frustrating, but different textbooks, different software packages have slightly different methods on finding the quartiles. StatDisk, which you will be using, will always give the same results as long as you have an even number of data values. All right, so now that we know how to find the quartiles, we can find this next measure of variation or dispersion that I mentioned earlier, which is called the interquartile range, or the IQR. Okay, so this is just another measure of variation or dispersion. Okay, and specifically, it is the difference between the first and third quartiles, or IQR is equal to the third quartile, Q3, minus the first quartile, Q1. Okay. And basically what it represents is the range of values over which 50% of the data is spread. Okay, because between Q1 and Q3 is where the middle 50% of the data lies. All right, let me go back quickly to the graphs we had here a couple pages previously. You know, between Q1 and Q3, we got 50% of the data. Q1 and Q3, 50%, and so on. Okay, so the IQR is literally this distance, okay, this quantity right here between Q1 and Q3, between which we have 50% of the data. Oh, sorry, I wanted to go back to this previous page where I know I've already erased this stuff on the screen, but you guys should have this on your paper. But let's calculate the IQR for these data sets. So for this first top data set, the IQR, okay, would be equal to Q3 minus Q1, which would be 27.5 minus 8, or 19.5. And for the bottom set, again, I've already erased it, but you have it. The IQR is equal to Q3, which is 28, minus Q1, which is 10, which is equal to 18. So again, it just gives us a measure of how spread out the data is. All right, so because quartiles are used to define the IQR, it is also a resistant descriptive measure. So let's just kind of summarize here. This is a table from the book. It's a really great summary of which descriptive measures we want to use and when. So for example, if the shape of our distribution is basically symmetric, either uniform or bell-shaped, then in general, we would report the mean, which, remember, the mean is not resistant, but in this case, we don't need it to be resistant because there's no extreme values and the distribution is fairly symmetric. So if we report the mean as our center, then we would correspondingly report the standard deviation as our measure of dispersion or variation, okay? And if we were going to check for outliers, and again, if we had a symmetric distribution, we would rely on the empirical rule and we would use z-scores to check for outliers in that case. Now, as we've seen in many cases, we might have a skewed distribution, whether it's skewed left or right. If it's skewed, then typically you're going to have extreme values on either end. And in this case, you would want to use the median as your measure of center. And the reason you would want to use the median is that it is a resistant measure. Okay? It is resistant to those extreme values, and it still provides a representative measure of center. And going along with that, if you're going to report the median, then you're going to want to report the IQR as your measure of dispersion or variation, because they go together. The median is Q2, the second quartile. The interquartile range is based also on quartiles. It's Q3 minus Q1. So they naturally go together, okay? And as far as checking for outliers, in this case, what we're going to do, which we haven't talked about yet, but we will right now, is you're going to use the upper and lower fences. All right, and these are based on the quartiles, and we will cover that right now. So again, a key point is that the mean and the standard deviation are not resistant measures. They can be highly affected by extreme values, And, you know, in general, if your distribution is very symmetric, go ahead and use the mean and standard deviation. You don't have these extreme values. You don't have an extreme skew. If you have an extreme skew and some very extreme values, then you're going to want to use the median and the IQR, okay? Because they are resistant to those extreme values. All right, so let's talk about outliers more now. We've already mentioned them several times. Basically, an outlier is a data value that is very far away from the other data values. It's extreme. It could possibly be the result of an error. Maybe you made some kind of a mistake when you were measuring or sampling or whatever. Or it could be just an unusually extreme data observation. That's possible too, okay? So what we want to do is we can use a numerical test to actually identify outliers, okay? And we're going to do this by calculating something called the fences. These are going to be cutoff points for determining outliers. And again, you would use this technique if you have a skewed distribution, okay? So the lower fence of a data set is calculated by taking the first quartile and subtracting 1.5 times the value of the interquartile range. Okay. That's the lower fence. And the upper fence is calculated by taking the third quartile and adding 1.5 times the interquartile range. Okay. So these are going to be basically our upper and lower boundaries. And then we will say that a data value is considered to be an outlier if it is below the lower fence or if it is above the upper fence. Okay? So basically what we're doing is something like this. We're creating a number line. We're going to calculate here the lower fence. And then up here we're going to calculate the upper fence. Okay. Anything above this is an outlier. Anything below this is an outlier. All right. And just this whole method for calculating the outliers seems to be a little arbitrary, and I did actually at one point look it up. And I found on a particular source, purplemath.com, which says, and I quote, "Why 1.5 times the width of the box," where again the width of the box is the IQR. So they're saying, why are we subtracting 1.5 times, or why are we adding 1.5 times the width of the box? Why does that particular value demark the difference between acceptable and unacceptable values? Because when John Tukey was inventing the box and whisker plot in 1977, and this plot is what we're going to do the following night in class, to display these values, he picked 1.5 times the IQR as the demarcation line for outliers. This has worked well, so we've continued using that value ever since. So literally, again, and we've seen this before in statistics, this whole definition is fairly arbitrary, but it seems to work, so we stick with it. Okay? All right, so I'm going to stop there, and we will go on with an example when we resume in class next week.